So I have just described one of many ways you can do the quantum key distribution. It was a very simplistic description of the whole protocol. Of course, there are all kind of nitty-gritty details that I skipped, but it just gives you the gist of the idea. To summarize it, essentially what it is about is for Alice and Bob to convince themselves that the qubits are prepared in this maximally entangled state, 0, 0 plus 1, 1. Tensor everything else. If this is indeed the case, that they are done, right? So because once they are absolutely sure that the qubits are prepared in this state, then all they can do is just to measure them in the Z basis, for example, and get perfectly correlated and random and also secret sequence of binary digits that can form a cryptographic key. The reason they are secret is simply because those two qubits are disentangled from anything else. So no measurement performed by an external entity will have any correlation whatsoever with any measurement performed on the two qubits. But of course, you know, the life is not that simple. So the first step in this protocol is really to run a public test in which Alice and Bob convince themselves that the state is what they expect it to be, or not, perhaps, right? So if they have a zillion of qubits, essentially the essence of the protocol is to pick up a random subset of qubits on which you run the public test for this state. So they say Alice is using her random number generator and says, "Hey Bob, let's run our test on this qubit, on this pair, and on this pair." And Bob says fine, and then they just go on and test for the average value of those operators. For they want to see the correlations x tensor x equal to 1 and z tensor z average value equal to 1. If this is really the case, if they see for every single randomly chosen pair, if they see the perfect coincidences, the perfect agreement in the measurements, the outcomes being identical, so they just have the perfect correlations, then they are confident that the remaining set of data that they didn't actually touch is also satisfying this condition, and therefore is in this state. So it's like a random sampling, right? So it's very unlikely, and of course you can run the calculations and you've Chernoff bound or whatever to make sure that you can quantify the fact that the probability that the remaining set of data doesn't satisfy this condition is actually very low. Implicitly, we assume here that each pair is prepared in an identical way, independent from each other. So this is like one tacit assumption that I haven't mentioned. So once they run the public test on a random subset, then they use the remaining subset to establish the key. So they just get the key from the set of pairs that they haven't used for the public test. Now, of course, you know, the life is hardly as simple as that. So quite often in real life, they will never see the perfect correlations. There will be always noise, not necessarily the adversarial noise. You see, it could be just the noise, because there is a noise, right? And so those values will be different from 1. So it will be 1 minus delta, 1 minus epsilon, for example. So they will have to work out for which values of delta or epsilon you can still distill secure key from the remaining data. So we're not going to go into those details, but the thing is that you can work out those values, and at some point Alice and Bob in public communication have to take a decision. If they think that the qubits that were taken to the public test passed the test, so if it is passed the test, then they just perform the measurements on the remaining qubits and establish the key. But it may also happen that the test is failed, right? So they see that this deviation from perfect correlations is too large. So if it is fail, well, in this case, they just abandon the key distribution and they try again. So I should mention perhaps that it is not the purpose of eavesdropping to stop Alice and Bob from establishing the key. On the contrary, an eavesdropper would like to fool Alice and Bob. So a good eavesdropper would like to make sure that Alice and Bob have the key, and he or she has also some information at least about this key. So essentially this is how the protocol works. What is in summary, all Alice and Bob want to do is to make sure that they have this particular state for each pair of the qubits. They do it by running a test, testing for perfect correlations on a randomly chosen subset of qubits. And once the test is, once those pairs of qubits pass the test, they use the remaining pairs to establish the key, because now they know that this is the state. So whatever, I can just measure in the Z basis and get the perfect correlations. If the pairs that are taken for the statistical test fail the test, then Alice and Bob have to just try again, or certainly they have to abandon this particular attempt. So the assumptions we made here, as I mentioned, that was that we assume that each pair is prepared in identical and independent way. And there is another assumption, namely that that Alice and Bob trust the devices, that they really know that they are working with qubits, that those devices are preferably made by someone whom they trust, and the devices are not doing dodgy things. We can actually drop these assumptions, and that's a beautiful thing. So we can talk about another test, which is related to the Bell inequalities. The test that doesn't actually require this assumption. So the devices almost can be just borrowed from anyone, even can be purchased from the adversary, and still Alice and Bob can actually get a good cryptographic key. So there's this new fascinating area called device-independent cryptography, or device-independent quantum key distribution in this particular case. But that's another topic.